My dear student, colleagues, and all the viewers watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. Today it's our 242nd International Physics webinar. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online International Physics webinar. We have successfully completed our 241st International Physics webinar. And today it's our 242nd, and today we'd like to welcome you all through a joint session between our Department of Physics, Pabna University of Science and Technology, and the Department of Physics, University of Notre Dame, USA. And we have with us here today Dr. Kenneth Cecire. He's currently working as a QuarkNet National Staff, University of Notre Dame, Department of Physics, USA. And he will talk about the remote data activities in particle physics education. So I think you will enjoy this session, and you can also ask question by commenting, and you can also join with us in our discussion session using the link. I will send the link in the comment section, so you can also join us. So our speaker have already connected with us, so I'd like to welcome our speaker, sir. Good morning and good afternoon. Good evening here, and welcome to our webinar, sir. So thanks for accepting our invitation, sir. And it's our honor and privilege to host you, sir.
Okay.
So you can start, sir.
Good evening, everybody.
Yeah, thank you, sir.
I'm sorry? Okay. If it's a good time to start, I will start.
Yes, sir, you can start.
So, okay. So good evening, everybody. And Dr. Das, please stop me if I speak too fast or I'm hard to understand. I have my American accent, so it will be maybe your students will be trying to adjust to that. So, so we are going to talk about remote data activities in particle physics education. Our program, QuarkNet, specializes in teacher professional development for high school teachers, and with a focus on particle physics. And in the past 2 years, of course, because of the pandemic crisis, many of our students have been, as in Bangladesh, have been remote, and we have connected via electronically, and so we have developed ways to do our particle physics activities remotely as well. So I'm going to just go over a few today, and we'll see how that goes. So here's our plan. With this introduction, we'll move to talk about a cloud chamber activity, our Quark puzzle, rolling with Rutherford, which is not really the Rutherford experiment, but it is inspired by the Rutherford experiment. And then using actual data from the Large Hadron Collider to calculate the mass of the Z boson. Okay, so what's this all about? Well, so first of all, we have to often explain why we do what we do, and basically, contemporary particle physics, the particle physics that's being done right now, and it's maybe no more than 10 or 15 years old. That's the cutting edge of science. That's what's new and exciting in science. It's not the only thing, of course, but it's a major part of that. And so that's naturally interesting and motivating for students. They may be taking a physics class, and then so it's their duty to study. But being actually able to examine data from actual particle physics experiments that are very recent or are still going on adds to their motivation and the excitement. And using actual data, we can use sometimes data that is simulated, and that's great. But when we use authentic data, that is data from actual experiments that puts the learners in the moment of actually doing physics. And then, once they and of course they can turn this around with it, because they're also learning a lot of great important physics in school. They're learning about the conservation laws. They're learning about forces in motion. They're learning about energy. And they can apply all of that to understanding the recent research. Conservation of momentum, for example, does not go away when you're doing particle physics research. As a matter of fact, it's extremely important. And they can apply that to understanding this research. So it actually not only introduces students to new physics, but it reinforces the physics, the basic physics that they are learning. And so we can do many of these activities, almost all really, remotely, when we can't meet face to face. Is face to face the best? Of course, but remote can work very well when we all work at it. Okay, so the first thing we're going to do is look at a cloud chamber. This is often, in many situations, what we will do to introduce students or teachers or others to what particle physics is all about. Because a cloud chamber is a very special device. They work best in a cool, dry environment, but they can work almost anywhere. And what they do is they create an alcohol vapor, a supersaturated alcohol vapor, by using a sort of an alcohol bath and a very strong temperature gradient. So, for example, you can see here in this diagram, it says solid carbon dioxide. What we usually call dry ice is very cold, much colder than water ice. And having that on one at the bottom, and then on the top having our alcohol soaked onto a cloth, and often sometimes we'll actually heat the top. That provides that really strong temperature gradient, and so the alcohol vapor that is created then becomes super saturated. It shows here an alpha source, which is great, but you actually don't need an alpha source for this to work. You can rely on particles that can be seen from the background, from cosmic rays and from background radiation, terrestrial background radiation. And the cool thing is you can actually build one. So now I'm going to try. Let's see what happens when I open this this link here. See what you see if you see something. Okay. So this page from CERN explains how to make your own cloud chamber, and this video is really, I think, a great example of that. Are you able to see that, or do you still see my PowerPoint?
Yes, we can see.
Okay, great. I'm not going to show the video now, but I am going to definitely recommend it. And let's see. Okay, so now we're back at the PowerPoint, and this one we are going to show. So when the cloud chamber is running, you can observe. You can actually observe it, and you can characterize the particle tracks for length, width, shape, and frequency. It's not easy. You have to really sort of observe carefully. We're actually going to take a look at a piece of a cloud chamber experiment that was done at Brookhaven Lab in 2007 by actually a colleague of mine, Helio Takai, who's now at Pratt Institute. Um, he was at Brookhaven at the time. So we'll get. So the nice thing is there are videos of cloud chambers online, and so you can. So if you don't have a cloud chamber or you cannot work directly with the students, you can actually still observe the cloud chamber. And so here, let's see how this will go now. I have to make sure okay, so there's some crazy music in the background, so I just let that go. But if you look carefully, you can see right now it's just some clouds, but suddenly you get these little traces. Okay, there go several. And they sort of appear quickly and disappear quickly. And so a student would observe this, and I would say two students working together would observe this. And they might say, for example, okay, there go a couple that are just little dots, and okay, there's a thin one. They might see a thicker one at some point, which is kind of fun. That's usually exciting. And they also notice that some are curved, but others are kind of curly, sort of bouncing back and forth. And if they watch enough, they can start to notate, okay, which one is which? What kind of particles are we actually seeing? So you can, of course, just seeing them is kind of neat. It's like, wow, I can actually see the traces of these particles. And the reason you're seeing that is because they're essentially making condensation trails in the supersaturated alcohol vapor. There's some really good ones right there. So I will stop this and we will go back again. So this is that's the sort of exercise or that students will do, and of course it's using actual data because those are actual tracks from particles. And what they find now, if they get really good at it, they have to practice a little bit. But they can see, for example, that when they get long, thin, straight tracks, those are likely to be muons. Muons are particles actually found in cosmic rays, and we're going to use muons later that are produced in the Large Hadron Collider in a different setting, a different activity. But muons are they travel. Basically, they travel straight through. They leave a trail and then they go. So they give a long, thin, straight track. And if there's a short, fat track, that's often alpha particles, which come from radon atoms, and radon is sort of all around. They're curly or zigzag. They could be electrons or positrons. And V-shaped tracks show particle decay because usually a V-shape means that a particle came in, let's say a neutral particle, which was not detected by the cloud chamber, but then it decayed into, say, a positron and an electron, for example. Now, with each of these activities, I have links to teacher notes and student guide that we have from QuarkNet, and so here the links are here and here. So I'm going to go back for a second and sort of re-explain something. This is be a quick jump back. This URL, and I will post this for you later in the chat, and I will certainly send it to Dr. Das. These same slides are in PDF form, and all of the links that we have in this presentation are there. So you can go to the slides, you can go to the links, and you can use everything that that we have available. Okay, and so let's go back. I just want to make sure you do that. Okay. So that's something that, when you think about it, if you are say you're working with some students because you were asked to tutor, or in a few years you might become a teacher, or maybe as a student you're asked to provide some outreach to high school students or in a village or a town, um, well, you can do something like this cloud chamber uh, as long as you have an internet connection between the two. You can do a cloud chamber program like this without actually having to build a cloud chamber, to go there and build a cloud chamber. You can actually do it remotely. Okay. Um, so another thing that we actually really enjoy doing, and it's a lot of fun, is called the Quark puzzle. And the idea of the Quark puzzle is that there are certain rules for making the quarks, for combining quarks. Now, the rules of the puzzle are based on these little tabs and little indentations that uh, the quark puzzle pieces have. So, for example, this spiky tab can't go into a round indentation, but it can go into a spiky indentation. This round tab can go into a round indentation. So you can combine them this way, um, and the only rules are you have shapes into which they are placed. I'll show you that in a moment. Um, and so you need to have no spaces in the middle when you combine the uh, the quark pieces. Um, you can have spaces on the outside, but and also you cannot have any overlaps. So you cannot have, for example, a tab overlapping a place where there is no indentation. So those are the rules of the puzzle. But then when you put them together properly, you can then look at, by reading things like the quark flavor, the electric charge, and the color charge, you can, and noting which one is matter and which one is antimatter. So, for example, this is bottom quark is matter, but this says up and then it has a line over it. That means anti-up, so that's antimatter. And this has a color charge of green. This one has a color charge of anti-red. So that's sort of how those things work. So you'll be able to work out those combination rules. Now, this, of course, is not using data. This is more on the introductory level, but it enables students to learn how quarks work, which we think is kind of fun. Um, so here is the sort of thing you can get, and this might help to see how they work. So, for example, if I wanted to make a pi plus, well, pi plus, there are two kinds of shapes we can fit into. There are the smaller meson shape, and which are these sort of hexagon shapes, and then the larger triangles are the baryon shapes. So mesons are combinations of two quarks. Baryons are combinations of three quarks. So a pi plus quark, for example, or positive pion, is a combination of an up and an anti-down quark. So that's matter and antimatter. And this charge here, all the charges of quarks are fractional. So this is plus 2/3 for the up quark and plus 1/3 for the anti-down quark. So the total charge is plus 1. And then you can see that the color charge is blue and anti-blue. By the way, what I mean by color charge is that physicists have figured out that quarks, as you know, quarks are the particles that combine to make the subatomic particles that we know, like protons and neutrons, but other particles too. And those quarks are attracted to each other by a force or an interaction that we call the strong interaction. It's strong because it's strong. It's easily overcomes the electromagnetic interaction, which sometimes might repel quarks, but the strong interaction will pull them together easily because it's so strong, at least at short distances. And that has its own charges. It doesn't have positive and negative charges. So physicists have characterized those charges using color. So red, green, blue, anti-red, anti-green, anti-blue are the color charges. So it's a bit of a more complicated system than electric charge or magnetic poles. Okay. Anyway, so you can see that's how we made a pi plus. A J psi particle, which is a pretty famous particle, is a combination of charm and anti-charm, and plus 2/3, minus 2/3. So the electric charge is plus 2/3 on one side, minus 2/3 on the other side. So this particle is actually going to be neutral. And then the color charge is green and anti-green. And anytime you have the same color but anti, so blue, anti-blue, green, anti-green, that means we say the color charge is also neutral. We call it color neutral. And then here's how a proton is made. We all know about protons. And so that would go into the baryon triangle here. And so the proton is a combination of up, and down. And by the way, with all of these, you can see the rules are applying, right? The tabs go into the indentations. There are nothing overlaps. There are no gaps, and they also fit into these shapes. So a proton is a combination of two up quarks and a down quark. And when you add those charges up, plus 2/3, plus 2/3, minus 1/3, it comes up to a charge of plus 1, which is what we would expect. Red, green, and blue, you may know that from combining light, shining lights and combining colors, red, green, and blue will give you white light. And so that, again, is color neutral. Okay, so let's take a look. So again, we have teacher notes and student guide. Let's take a look at the puzzle itself. We'll see if this works. There we are. Okay, so if I wanted to make a baryon, so let's say I want to make a meson, that's at the top here. Let's say I want to start with a strange quark. That's great. So I put the strange quark and fit it right in there. That was pretty easy. But now if I want, let's say maybe a strange goes with a bottom quark, and I can right click and turn this around. Well, that's not going to work. There's going to be an overlap there that's like, no, 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 no. So let me try maybe an antibottom. Well, that sort of doesn't work either, but maybe I need a different kind of antibottom. So let's try this one. We're getting closer. Still not there. Let's try this kind of antibottom. And that works. And so now I don't know exactly what the name of this interesting particle is, but I know it's a strange antibottom. And I know its charges looks like minus 1/3, plus 1/3. So its electric charge is 0. It's neutral. And red, anti-red. So that would mean that it's color neutral as well. And if I wanted to make a baryon, I can do the same thing. I can maybe start with an up quark and let's see how that's going to go in there. Maybe like this. Nope. Like that, maybe. Yep, that'll work. Okay, and let's say I get a down quark. Let's get a green down quark there. Let's see. That works. And You may be saying, oh, I know what he's up to. He's going to get a red down quark next. And you're absolutely right. You caught me. And the reason you know that, of course, there we go. Takes me a while. Is because we know that up, down, down makes a neutron. So I used, in this case, I kind of cheated. I used something that I already knew, so I could quickly make a baryon. But that's how the puzzle works. What the students do is actually, by the way, you can, if you are looking for the names of the particles you create, that's not the main purpose. It's not to say I made a JSI or I made a pion, but rather it's to learn the actual quark combination rules, learn something about the names of the quarks themselves and their characteristics, and how mesons and baryons are made. But you can go to the particle data book online, and you can look up these different combinations. And that's always might be a nice thing for students to do outside of their regular class time in order to deepen their understanding. Oops, I didn't want to quite go away from that yet. There is also a results table. I just want to show you that briefly. Okay, and by the way, see, this is a Google Sheet, so you would make a copy. Okay, it's working. Google is taking its time. So there it is. So I've already put in a couple of things that we've done already. So we did an up, anti-down. So these are mesons. So this is our up and anti-down. This is the pi plus we made. And this is the J psi we made. And so I just filled in everything about that we have about these. And this is our meson table here. So 2 quarks with 2 color charges. And there's a net color charge is neutral and neutral. Then an electric charge. And whoops, that's incorrect. That electric charge would be 1. Okay. And that's a net electric charge, and net electric charge is 0. So as students build up information on this, they can do the same thing in the baryon table. And here, the net electric charge is 1 also, by the way. They can, as they build that up, they can start to say, okay, well, what's the pattern? Is the net color charge always neutral, or is it sometimes something else? Is the net electric charge always neutral, or is it always 1? What's the pattern? So that's the idea, and that's what they're trying to find out. Okay. So, Dr. Das, are we able to stop for questions, or should we go to the end?
Discuss the question later. We can discuss the question later, sir.
I'm having trouble understanding.
Can you hear me?
I cannot really hear you. No, just a little bit.
Can you hear me?
Yeah, I hear you now.
Okay, we can discuss the question later, sir.
Okay, good.
Okay.
Thank you. Sorry about that. Just wanted to make sure that I understood. Okay. So the next one we're going to do is called Rolling with Rutherford. It's not really the original Rutherford experiment. For one thing, we don't have a gold foil, but it's inspired by the Rutherford experiment. And in particular, we believe the Rutherford experiment in many ways, at least I believe, the Rutherford experiment is the prototypical particle experiment. And what do I mean by that? Well, when you want to understand something, and you can't measure it directly. Let's say, for example, there's something across, on the other side of a fence, and you don't know what it is, and you can't see it, but you've got lots of oranges in your yard. So you throw oranges over the fence, and you hear when they hit, and you hear when they miss, and because when you hear when they hit, they go bong, And then when they miss the object, they don't make a sound. And so you start to get an idea, well, the object's about this size. And so basically we throw things at things to understand them. And that's what Rutherford did. He used a collimated beam of alpha particles. He threw alpha particles, essentially, at a target. There's always a beam, and there's always a target. And so in this case, the target is a gold foil. So he was looking at actually what happens when alpha particles encounter gold atoms or do not encounter gold atoms, which is just as important. And then he was able to, by seeing the pattern of uh, interactions, deduce that sometimes there was a very hard scatter of the alpha particles, which meant they must be hitting something that was small and dense. And so he understood then that the atom actually has a nucleus surrounded by something. Well, we now know electron clouds or electron wave functions. And so more often than not, the alpha particles would miss the gold nucleus, but some would hit. Okay, so that's, but we're going to use it in a slightly different way. We're going to use, what we do normally is, as you can see here with these students, they would roll marbles at an array of other marbles, and then they would listen to see when they hit, and they could also see them bouncing out when they hit. So they would then determine how many each student would roll 10 times. They would determine how many hits they got out of 10. And when you think about it, the bigger the marbles are, the greater the probability of a hit. The smaller they are, the less the probability of a hit. So they could actually, each student would take their own results out of 10, and they would build a histogram. And here's an example of a teacher in Rwanda building I think this was in Rwanda, yeah, a teacher in Rwanda helping to build a histogram by using Post-it notes. So he took his result and he placed a Post-it note for his result onto the histogram. And so we could see there was eventually a peak and say, oh my, there's the most probable number of hits out of 10. And we use that to figure out the probability of a hit. And then we can use that to figure out actually the size of the marble. Now, why would we do this? Well, because if physicists are trying to understand the size of, say, protons, they cannot measure them with a caliper. Protons are much, 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 much too small for that. Their nature doesn't even allow for it. So but by throwing other particles, perhaps other protons, at them, they can determine the size of the proton that way. At least get a good estimate. And so that's what we do in this experiment. So here is the basic idea. We have 5 target marbles, and we throw 10 different times. And from 10 different places, we roll our projectile marbles, and then we count the number of hits. And of course, every student who does this will get a different result. And so now we can do this in person, but we can also use this sort of simple simulation that a colleague of mine wrote. And you can see here, there go the marbles, and there's a barrier hiding the actual marbles that would hit, the target marbles. That's what I was trying to say. It hides the target marbles, so there's no sense of aiming or anything like that. So you can see we do it again, and the same thing. And we count the number of marbles that hit, and ignore the marbles that don't. And so you can see here there are 1, 2, 3, 4, 5, 6 marbles. Looks like 6 marbles hit, and then you do it again, and this time 3 marbles hit. And so each time you do it, you record the number of marbles that hit, um, and and each of those makes a data point that goes into your histogram. Now, this is the way I usually collect this data. I have a Google form, which you can check out later. The Google form actually, sorry, just checking my time here. Okay, good. The Google form actually enables the students to put in their results, and if they can, and then we can build a histogram from all of the students' results. And the sort of result you get is something like this. You get a histogram, and the way I analyzed it was I said, well, look, the greater the probability, the greater the diameter of the marble, the greater the probability. So the probability depends on the diameter of the marble. Well, it also depends, though, on the number of target marbles. More target marbles means more hits. And the probability also depends upon how wide the area is that you're rolling the marbles in. So if they're constrained, there are more hits. If it's open, there are fewer hits. Okay. But then we realize that, well, yeah, but a marble can hit, doesn't have to hit straight on. It can hit at the very edge, and that's still a hit. So in fact, oops, I should have typed 2D here. This diameter is actually, this distance is actually 2D. So I apologize for my mistake in the diagram. So where you see 2D here, that should also be here. So in fact, because there's a radius, a diameter, and another radius, so that's 2 diameters. So if I can correct my equation, say, well, the probability of a hit is the number of marbles times twice diameter divided by, and then I subtract the diameter from the width, because the marble can also hit the edge of the beam area, and but its center never gets closer than 1 radius from the actual wall of whatever's of the of the structure that's holding the beam area together. And so if that happens on the other side, that's 2 radii, so you have to subtract the diameter again. Sometimes I leave this other part out, the subtracting the diameter, because it's not as big in effect, and it's a little harder to explain. But when I put in the numbers that we have, so I took this is from the African School of Physics in July 2021. We actually did it online because that's how we met. And I said, based on this histogram, I said, well, probability is 6 or 7, so I'll call it 6.5 out of 10. So, and again, that should have been 6.5 out of 10. I guess I was a little hasty when I was typing this up. So, so 6.5 out of 10 equals 5 times 2d over 30 centimeters minus d. And so when you do the arithmetic here, it's 2.1 centimeters. I will correct this, and I will post the corrected version. So my apologies for that. Okay. But in any case, I know the number is correct because I did it on paper first. So the final result. So you say, well, how do you know if it's really 2.1 centimeters? You could go ahead and measure it with a ruler or a caliper at that point, but recognize that if you're actually measuring a proton or measuring the size of an atomic nucleus, that option would not be available to you. You have to rely on this kind of indirect method of measurement, and that's, of course, what we want the students to learn about. Okay. So last one, and I realize I've been using up more time than I expected. I tend to talk a lot. Uh, so we'll go through that and we'll get it done within hopefully a few minutes. Is measuring the invariant mass of the Z boson. The Z boson. If you look at this chart here of the standard model of fundamental particles, here are the quarks that we were playing with in the quark puzzle. These particles here are leptons, so the electron, muon, and tau. We mentioned the muon before because you can see them in cloud chambers, but you can also see them in particle physics experiments of other kinds. And the Z boson is an interaction particle. It's sometimes called a force carrier. And it's actually a particle that carries the weak nuclear force. So the strong nuclear force is the one that holds quarks together. The weak nuclear force or weak nuclear interaction is what enables radioactive decay. And in the 1980s at CERN, the W boson and the Z boson were discovered. And then in the Large Hadron Collider, um, the one of the first things they did was study the production of Z bosons to see if the accelerator and the detectors were properly calibrated. Because if they get a mass of the Z boson that's different than the previous experiments, then they know something needs to be reworked. If they get fewer Z bosons than they expect, or more Z bosons than they expect, then again they have to do something. They have to recalibrate their detectors, or perhaps tweak the beam. So the Z boson was sort of used as a standard candle for measuring, for calibrating the Large Hadron Collider, which is the big collider now at CERN. By the way, the Large Hadron Collider uses the same principle from rolling with Rutherford, from the Rutherford experiment, a beam and a target and a detector. The differences here, the beam and the target are the same thing because you are colliding protons. So the protons coming in one direction are the target for the protons coming the other direction, and vice versa. So, okay. So when protons collide in the Large Hadron Collider, sometimes they produce Z bosons. The Z bosons decay very promptly. They never make it outside of the beam pipe. They are not detected by our detectors directly because they have such short lifetimes. Even moving at the speed of light, they only go perhaps the less than the diameter of an atom before they decay. So we don't see them directly. But they can sometimes decay into a muon and an anti-muon. So a muon and its antimatter partner. And which we sometimes just call muons because we're not really interested in whether it's matter or antimatter. We're just looking at the tracks. And we can use the momenta and the energies of those muons to work backwards and figure out the mass of the Z particle that we cannot observe directly. And now, when protons collide, they will produce Z bosons which have some momentum of their own, which could be in any direction, which means that the muons could be going off in any direction. But what we did for this measurement was we only selected events in which the muons happen to be perpendicular to the beam line, which means they're in what we call the XY plane. So you can see this is an event display from the CMS experiment, compact muon solenoid experiment. Protons come in this way, they come in this way. There's a collision, lots of stuff happens, but these long tracks here are the tracks of muons because muons are long-lived particles that relatively don't interact much, and so they make it all the way outside of the detector, and they cross these muon chambers here, and so we can look at them this way. But in this case, though, we're only going to look at those which happen to be perpendicular to this beam line. And so why do we do this? Well, students have to use vector addition to make it work, conservation of momentum and energy, and a little bit of relativity, one equation, but it's an important one. And they get the event from here. This is our Z data. And we actually have 4 events from ATLAS, the ATLAS experiment, which is on one side of the Large Hadron Collider, and 4 events from the CMS experiment, which is on the other side of the Hadron Collider. And students can pick one. You might ask 2 or 3 students to work together, and they can each pick one of those. Now, because the data is essentially on a PDF, they can measure it. If they have a computer at home, they can measure it without you having to hand them a piece of paper. So that's kind of the fun of it. In fact, the one they're going to measure, in this case, is this one here. And you can see here are the 2 muon tracks. And this is a sort of a secondary effect that would not of interest to us, but 2 muon tracks in red here are what we're looking for. And we will use this information. And you can see you're given a momentum for each track that's been measured. And so we'll use this information to work backwards and find the mass of the Z boson. Okay. So, by the way, we call this invariant mass because some people talk about in relativity about mass changing with velocity. Particle physicists don't like to do that. They refer to the invariant mass, and that is the mass in any reference frame, which means it's the what other people might call the rest mass, but it's really the mass, the actual mass of the particle. Okay. So we picked event D, and then what the students have to do is they have to measure the angles that these 2 muon tracks come out at. So now, of course, when you're with them in a classroom and you can hand them protractors and pieces of paper, and they can make those measurements. When they're at home, they might have a protractor and they can put it right on their screen. But if they don't, here's a hint. These radial lines for CMS are 9 degrees apart. So you could estimate the angle by counting the radial lines. Also, Chrome has a protractor extension that can be downloaded. And there's the download. And estimates are still work. And often what we do is we get a lot of students to do this measurement, and everyone will get a slightly different number because they make different estimates. They place things a little differently. And so we end up with a nice histogram. So in this case, I measured it using counting the radial lines method. And I decided that theta 1 for the first muon is 207 degrees, and theta 2 for the second muon is 267 degrees. Okay, so buckle in. We're going to do a little bit of arithmetic. So first, we measure we get the muon momentum components, and we do that using a little bit of trig. So we say P1x for the first muon is P1 cosine theta, P1y is P1 sine theta. We plug in the momentum in these units, GeV over C, giga electron volts, divided by the speed of light, times the cosine of the angle. And we get these results for the x and y components for P1. So the x component is there. There's the y component. And then for P2, we do the same thing, except we start out with 70.1 GeV and an angle of 267 degrees. And you can see the x component is just a little bit, as you can see in the diagram. And so that's minus 3.7 GeV, but the y component is minus 70. Okay. So we found the muon momentum components. Great. What are we going to do with them? Well, we can add those components to get the momentum, the x and y components of the momentum of the Z boson. Why? Well, because the Z boson decayed into those two muons, the momenta of those two muons comes from the momentum of the Z boson. So by adding up the X components, we get the X momentum of the Z boson, and adding the Y components, we get the Y momentum of the Z boson. And then we can calculate the square of the magnitude of the Z boson momentum. So of course, then we can take the square root of that and get the actual magnitude of the momentum. But actually, we only need the square of it for our calculation. The energy of the Z boson, by the way, energy. Now, this is an interesting thing, which is sort of a combination of how units work and how units work in particle physics, and also the fact that the energies are great and the masses are very small for the muons. So we can, the same numbers that we took for the momenta of the muons are also the numbers for the energies, but we get rid of this over C business here. So, and then because energy is not a vector, we just add them straight away. 139.5 plus 70.1, 209.6 GeV. We'll need the square of that, so we square it. Okay. Why do we do that? Well, we do that because the energy mass momentum relationship is E squared equals P squared C squared plus M squared C fourth. But by the way, if P is much bigger than M, then this term goes away. And that means E equals PC, and that's why we can do that with the muons. You can't do that with the Z boson itself because its mass is much more significant. Okay, so we're going to apply this to the Z boson now. So the energy we calculated squared was this. The momentum we calculated squared was this. And then you notice we have a C squared and we have over C squared in the units. Those cancel out. Woohoo! So we end up still with GeV squared. And then we can solve for M squared C fourth, take the square root and get M C squared. And so then M is 98.9 GeV over C squared. Or since particle physicists don't tend to just say GeV all the time and stop saying C squared and C, then we just say the mass of the Z boson is 98.9 GeV. Turns out the average measured mass of the Z boson is more like 91.2 GeV. So we're in the right neighborhood, but we're not in the same house. That's okay. You'll find that if you do enough of these, some will be closer, some will be farther. And in fact, in particle physics, it turns out that saying the published mass of the Z boson is 91.2 GeV doesn't mean that every Z boson has a mass of 91.2 GeV. They will vary because of quantum mechanics. So, so we got a pretty good answer, and that's the point. Now, there is, if you click here, this goes to a Google Sheet that allows you to do the same calculation almost instantaneously. You still have to measure the angles, but aside from that, you can do the same calculation pretty quickly with using a Google Sheet. Okay, so you can find more in the QuarkNet data activities portfolio. We have lots of activities, and then we have notes on remote learning adaptations to these activities at this link here. And that is all I have to say, aside from our discussion. So I will stop sharing for now. And I will stop this. And there we are. Oh, it was an hour. How about that?
Yeah, thank you, sir. We have one question in our comment section. So The question is, do you have any remote data activity related to neutrino physics?
Nuclear physics?
Neutrino. I
Yes,
can
we
add
do
the
that.
question.
Yes. We have, first of all, we have what we call a master class in neutrino physics. And let me see if I can bring that up first of all, because that's kind of fun. So on our website, um, we have uh, the Minerva masterclass. Minerva is a neutrino experiment that recently concluded at Fermilab, and I guess I won't go through the whole thing here, but um, it enables you to actually. Let me go down here to show you. You can actually um, look at. Uh, that one's empty, but that's okay.
Maybe
You can look
you
until
have
you
to.
find something. Well, I won't get into the details here, but there's something like this. This is a shows a muon and a proton which were knocked out of a nucleus by a neutrino. So we do have those activities. They are in they're also also if you go to. So I apologize for that.
Okay,
Let me just go to.
okay, sir.
Okay, let me share for a moment again.
Yeah, you can.
Okay.
Yes, we can
So
see.
this is our main page over here. And if we go to master classes, neutrino project map, that takes us to the neutrino master class. If we go to data activities, that's our data
Okay,
activities portfolio. And if I go to curriculum topics, um, there are quite a few here. We don't have neutrino in directly, but we have a neutrino strand actually. And so these are all neutrino related activities. Some are more closely related than others, um, but they're all sort of leading to understanding neutrinos. So there's the answer. Okay, sorry.
okay, thank you. So as we have discussed earlier that we can arrange a workshop about this so that student can interact with you in this remote data activities. So and they can directly communicate with you. So thanks again for giving us this time. It was a great opportunity for our student and the viewers. I think they have learned a lot of things about the remote data activities of particle physics education, and hopefully in near future we can arrange another webinar and workshop with you. So thanks again, sir. So
Well,
it's
thank you.
an honor for me.
Yeah, I enjoyed it, and I hope if we have a workshop, I can talk more directly with the students, and
Yes,
that would
yes,
always
that
be
will be
fun.
better, sir. Thank you. Bye
Okay,
for
thank
today.
you.
Yeah,
Okay,
have a nice day, sir.
have a good evening.
Bye.
Bye bye.
Yeah, bye bye, sir.